Hi, I'm Jodie from EdGenie and I'm going to be taking you through the Edexcel October 21 mechanics paper. After each question, I'm also going to be looking at the examiner report to see what common errors students made. So question 1 says a particle P moves with constant acceleration 2I minus 3j. At time t equals 0, P is moving with velocity 4I, so that's going to be our u, isn't it? Find the velocity of P at time t equals 2. Okay, so to do that, we're going to use our formula. So it's V equals U plus AT. So our U is going to be 4I plus our acceleration multiplied by t, which at this point is going to be 2. So now we just need to work that out. 4i plus, and then we've got 2i times 2. So 4 plus 4, that's 8i. And we've got minus 6j. Okay, and that's our answer for part A. Part B says at time t equals 0, the position vector of P relative to the fixed origin is this. So basically it means we're not starting at the origin, we're starting at I plus j. Find the position vector of P relative to the origin at time t equals 3. So we want to use our formula, which is ut plus half AT squared. But because we're not starting at the origin, I'm first of all going to add I plus j. Then I'm going to apply this formula. So U, we said, was 4i multiplied by t, so at this point it's 3, plus a half times our acceleration, which is 2i minus 3j multiplied by 3 squared. So let's put this into our calculator. So the I values, we have got 1 plus 4 times 3 plus, be a bit careful here, we've got a half times 2, so they're going to cancel out and be 1, multiplied by 3 squared, which is 9. So I'm going to add 9. So that's given me 22i. And for the j values, we've got 1 here plus. So we've got a half times negative 3 times 3 squared. And that's given me negative 25 over 2j. So the examiner report said that question 1 was actually answered really well. Quite a few students actually integrated in part A, but that's fine. You can get the correct answer doing that. Part B wasn't done quite as well as part A because quite a few students forgot to add the I plus j. Question 2. So a small stone A of mass 3m is attached to one end of a string. So that means that we've got our weight here, which is going to be 3mg, don't forget the g. A small stone B of mass m is attached to the other end, so that's going to be m times g. So what this means is because A is heavier than B, when it's moving, it's going to go down like this. So this stone is going to go down and this stone is going to go up. Initially, A is held at rest on a fixed rough plane. So that means we're going to have friction. So because this stone is going down the slope, we're going to have friction acting in this direction. The plane is inclined in the horizontal, okay, and they've said tan of alpha is 3 over 4. So that also is very helpful. So remember, if it's tan, the opposite over the adjacent. So this is the opposite, so that's going to be 3. The adjacent, so that's going to be 4. So this length here must be 5. Remember, 3, 4, 5. Right, the string passes over a pulley that's fixed at the top of the plane, up here. The part of the string from A to P is parallel to a line of greater slope. Yeah, that's fine. Stone B hangs freely. The coefficient of friction between A and the plane is 1/6. Stone A is released from rest and moves down the plane. The stones are modelled as particles. The pulley is modelled as being small and smooth. The string is modelled as being light and inextensible. So that means we have tension. Tension here, and it's going to equal this tension here. Using the model for the motion of the system before B reaches the pulley, write down an equation for the motion of A. So the first thing we need to do before we can do that is resolve our forces. So we want to know what this is going to be, and we want to know what this one is going to be. You might be able to see that this is going to be 3mg sine of alpha, and this one's going to be 3mg cos of alpha. If you can't see that, then you just need to draw the triangle. So this is 3mg, then we have this line here, which is 3mg cos alpha, and then we have this line here, which is going to be our 3mg sine alpha. But if you're not sure why, it looks like this. So this is going to be our opposite, and this is going to be our adjacent. Then, so what are we doing? We need to do this force minus these two, and that's going to equal our mass times our acceleration. So minus our friction, minus the tension, and that equals our mass times our acceleration. So that is from your F equals ma. And that's actually all we need to do for the first one. We don't need to figure out what F or T or anything is, so we can just leave it like that, and it was only 2 marks. Part B, show that the acceleration of A is 1/10g. So I'm going to do some more resolving here. So first one I'm going to do is up and down, looking at the stone B. So because the stone is going upwards, I'm going to do tension minus mg equals mass times acceleration. Okay, and we can also resolve in this direction. Let me show you. So we have got one more force I haven't put on yet, this one here, and that's going to be your reaction force. So that's basically the slope pushing the stone away. And that is going to equal 3mg cos alpha, because obviously the stone isn't falling through the slope, is it? So these two must be equal. But we also know that F equals our coefficient of friction, which was 1/6, multiplied by R. And R, we now know, is 3mg cos of alpha. And what is cos of alpha? Let's have a look. So on our triangle, to find cos, we do the adjacent over the hypotenuse. So it's going to be 4/5. So let's put this all into our calculator. We can actually do that in our heads, can't we? Because it's going to be, this is a half times 4/5. So it's going to be 4/10, which is 2/5. And let's also rearrange this. Let's write this as T equals ma plus mg. And now we can substitute everything into here. So we are going to have 3mg sine of alpha. Let's go back up to my triangle. So we're going to do the opposite over the hypotenuse, so 3/5. minus F, which is 2 over 5 mg, minus our tension, which just be careful because we're minusing that, so it's minus mg minus ma. Sorry, minus ma minus mg, and that's going to equal 3ma. Now let's do some rearranging. So let's divide everything by m. Then, can you see these terms are all with g? And then this one's a. So if I add a to both sides, I'm going to get 4a. And then over here, I've got 3 times 3 over 5 minus 2 over 5 minus 1, all multiplied by g. So let's put that into our calculator. 3 times 3 over 5 minus 2 over 5 minus 1. That's given me 2 over 5. So we've got 2 over 5 g equals 4 over, not 4 over a, equals 4a. So a is going to be, if I do 2 over 5 divided by 4, it's going to be 1 over 10g. And I remember that, yeah, that's what we were trying to show. So we've done it, we've got the 7 marks. Just be careful though, because this is a show that question, we did need to write everything out in full, which we did do, so that's great. Sketch a velocity time graph for the motion of B from the instant when A is released from rest to the instant just before B reaches the pulley, explaining your answer. And it's 2 marks, so I know I'm going to get 1 mark for the graph and 1 mark for explaining my answer. So the graph is going to be pretty simple. It's going to be, so we've got time, we've got velocity, we start from rest, we've got constant acceleration, so it looks like this. And for my briefly explaining, I'm just going to put constant acceleration. And part D. In reality, the string is not light. State how this would affect the working in part B. So if the string is not light, then that means that this tension here and this tension here would be different. So I can just say something like, tensions would not be equal. And that's it. So the examiner report said that candidates need to make sure that they read and then answer the questions carefully. And they go on to say how in part A, instead of just doing the small equation that we did, they modelled the whole system. So make sure you read the question and you look at how many marks you get. Errors in part A were mainly due to the omission of the relevant force or a misunderstanding of direction, so not understanding which way the stone falls. So question 3, a beam AB has mass m and length 2a. The beam rests in equilibrium with A on a rough horizontal ground. So this ground here is rough. If you think of it, they've not told us it's a ladder, but imagine if you have a ladder against a wall, if there's friction, it would stop it slipping. So our friction is going to act in this direction here. The beam is inclined to the horizontal and angle theta as shown. The coefficient of friction between the beam and the ground is mu. The beam is modelled as a uniform rod. So if it's uniform, that means that the weight is acting in the middle. So it's going to be like this. And it said it was M, so that's mg. So it's perpendicular to the wall. Okay, using the model, show that our coefficient of friction is greater than or equal to a half cot theta. So because it's cot, we're gonna probably at one point have like cos over sine, aren't we, to get to cot. So it's 5 marks. There's going to be a bit going on here. let's resolve our forces, and then we can take moments at different points and then see where we get. Right, let's look at this mg first of all. So we're going to have a force here, and we're going to have a force going down like this. This one is going to be mg cos of theta, and that's going to be mg sine of theta. We also have our friction here. So this one is going to be F sine of theta. And then going up in this direction, we're going to have F cos of theta. And if you're not sure, you can draw that out. So that's not a very straight line. There we go. And we have got, let's think how I'll draw this. That would be our right angle. This angle here is our F. So you need to have a think about where theta would be. And in this case, theta is going to be over here. So this one would be our cos, and this one will be our sine. We're also going to have our reaction forces. So we're going to have one here. I'll call that R1 against, so it's perpendicular to the ground. And we're also going to have one here, which is perpendicular to the wall. So I'll just call that R2. So we also want to resolve this going down, like along the slope. So this one, let's change colour. Let's do purple. We're going to have one going like that. And we're going to have one going like that. This one here is going to be R2 cos of theta. And this one is going to be R2 sine of theta. Okay, and then this one here, we're going to have one going up the slope like this. And we're going to have one going at a right angle to the slope like that. This one's going to be R1 cos. And that one is going to be R1 sine. So actually answering the question now, show that, so our coefficient of friction is greater than or equal to a half cot of theta. I'm going to take moments about A, because look at this, like what a mess this is. So if we take moments about this point, we can basically ignore all of the forces at that point. So we're going to have none here, and then along here, we're going to have A, because this distance is A, multiplied by mg cos of theta. And then we're going to have 2a times r2 cos of the sine of theta. So let's write that out. We are going to have a times mg cos of theta equals 2a r2, is it sine of theta? Let's go and check. That's cos, that's sine. Yeah, correct. Then let's also resolve up and down. Let me just write here actually. That one's moments about A. So any forces going up and going down. So we have a force here going up and we have a force here going down. So R1 must equal to mg. And when we resolve going left and right, let's go and have a look. We are going to have F going in this direction and R2 going in that direction. So F must equal R2. And we also know that F is going to be less than or equal to mu R. So, and that's going to be R1 because we're just at that point of moving, aren't we? So let's substitute in all our values. So F is equal to R2. Our coefficient of friction times mg. So now we need to work out what R2 is, and then we can substitute back in here. So let's rearrange all of this one. This is our moments about A. So if we, what should we do? Should we divide everything by A? Yeah. So we're going to have mg cos theta equals 2 R2 of sine theta. So let's divide this. This is going to be a half mg cos theta over sine theta, and that's going to equal R2. So now we can rewrite this. We can do a half mg, and let's rewrite this as cot now. Divide both sides by mg, and I think we've got it. Was that the answer? Yeah, there we got it. So therefore, it's a half cot of theta is less than or equal to mu, and you're done with that part. So part B says a horizontal force of magnitude kmg, where k is a constant, is now applied to the beam at A. This force acts in a direction that is perpendicular to the wall and towards the wall. So it's going in this direction here. Given that, and we've got tan of theta equals this, and we've got a coefficient of friction, and the beam is now in limiting equilibrium, use the model to find the value of k. Right, let's do this then. We're going to need to draw a new model, unfortunately, because that is going to change quite a few things. I'm not going to draw the whole thing again, but I'll draw some important parts. So this, what was it, kmg? Yeah, and so that's going to be kmg. And then this way is now going to be our friction, because it's going to be acting in the other way to the force. So it's going to be our coefficient of friction, which we said was a half, and that's going to be multiplied by R1. Let's put the R1 down there. Okay, so now let's take moments about A, like we did before. This bit is going to be quite similar. So it's going to be 2a times R2 sine theta equals 1a mg cos theta. So that one's going to be the same. Although last time I think we had friction, did we? Oh no, we did have that. Okay, so 2a times mg, times R2 sine of theta equals a times mg cos of theta. Now let's go up and down. So we've still got this force going up, and we've still got this force going down. So R1 equals to mg. Okay, now let's go left and right. This one is going to be different. So for this one, we've got half R1 going this way, kmg going this way, and let's have a look if there's any others. So we've also got this R2 going in this direction. So it's going to be R2 plus half R1 equals kmg. Hopefully this is going to be enough information. I can't see why we would need any more, because we've got R1 as this, R2 we can get from this, and then we can find out what k is. So let's substitute in a few things. What else did they tell us? They told us tan. Let's call this theta. So tan, what did they say it was? 5 over 4. So that means our opposite is 5 and our adjacent is 4. It might work out well again, actually, that we'll just divide. So I won't actually find out the value for sine and cos just yet. Right, looking at this, let's divide everything by a. We are going to have 2r2 sine theta equals mg cos of theta. Then let's divide, we want R1 to be the subject. So, R2 to be the subject. So R2 is going to be a half mg cot of theta. Okay, and we can actually rewrite this as a half mg cot. So cot was going to be 4 over 5. Or we can rewrite this as 4 over 10, which is 2 over 5 mg. So now I'm going to substitute it into here to find out what my k is. So R2, which is 2 over 5 mg, plus a half R1, which is mg, equals kmg. That's worked out quite nicely. Divide everything by mg. 5 over 2 plus a half is 9 over 10, or 0.9. So that is our value for k. Let's just go back and check that we've answered the question. Use the model to find k. Yes, so we have. So the examiner report said that Part A required candidates to show that. Consequently, full marks were only awarded if there was a fully correct solution with all the steps included. So it sounds like they were really strict with this, and you need to make sure that you literally write out your full equation before you do any simplifying. So let's have a go at question 4. A small stone is projected with speed 65 from a point O at the top of a vertical cliff. And they've said that this point is 70 meters vertically above point N. Point N is on horizontal grounds. The stone is projected at an angle above the horizontal, and they've given us the tan. The stone hits the ground at point A as shown on figure 3. The stone is modelled as a particle moving freely under gravity. And it says acceleration due to gravity is modelled as having a magnitude of 10. So that's really, really important because that's going to affect the whole question. So the question says, using the model, find the time taken for the stone to travel from O to A. So we're looking for the time. But what we're going to need to do first is write out our suvat in 2 different directions. So we've got one direction going up and down, one direction going left and right. So we know when we're going horizontally, we're not going to have an acceleration. So that's going to be 0. When we're going upwards, we're going to have an acceleration which is going in the opposite direction of gravity. And they've told us that in this case, we're taking it as 10. So it's going to be negative 10. We also know that the speed is going to be at 65. So if I take my speed in this direction and also in this direction, this is going to be 65 cos, and this one's going to be 65 sine. So 65 cos, 65 sine. And we want to find the time taken for the stone to travel. So if we're starting here and our height is at 0. When we get here, our height is going to be at negative 70. So we're going down 70 meters. Right, let's do it. Should we use S equals UT plus half AT squared? So let's substitute in our values. So minus 70 equals U, which is 65 times sine. Let's have a little think about these for now. So what have they told us? Okay, so tan is 5 over 12. So that means that the opposite is 5 and the adjacent is 12. So that means sine is going to be the opposite, which is 5, over the hypotenuse. So let's work out what that is. So I'm just going to do the square root of 12 squared plus 5 squared. So that gives me 13. So sine is opposite over hypotenuse, and cos is adjacent over hypotenuse. We don't know if we need that yet, but well, we do actually. We definitely do. We need the sine one now, which is 5 over 13. Okay, so that was my u, 65 times sine of alpha, which is 5 over 13, multiplied by t, which is what we're trying to find, plus half times my acceleration, which is minus 10, times by t squared. So let's multiply this out, and then we can solve. 65 times 5 over 13, that's going to be 25, so 25t, and here we're going to have minus 5t squared. So we can divide everything by 5, but also I want to take the minus 5t squared over this side to make it positive. It's going to be a bit easier for me. The minus 25t minus 70. Just so that when I factorise it, it's going to be way easier. So let's divide everything by 5. 70 divided by 5, that's just going to be 14. Yeah, so look, we can already see that it's going to be 7 and 2, isn't it? Minus 7, positive 2. So therefore, t is going to equal 7 seconds. So that's part A done. Part B. Find the speed of the stone the instant just before it hits the ground at A. So we're basically trying to find out if t we now know is 7, what is v? Right, well we know that the speed is going to be constant when we're looking horizontally. So that's going to be 65. So let's write it like this. That's going to be 65 multiplied by, and it was cos, which was 12 over 13. Let's put that into our calculator, see what we get. So 65 times 12 over 13, that's given us 60. So now we need to do vertically. So let's do v equals u plus at. Would be easier, wouldn't it? Substitute in. So our u value we know is going to be 65 times 5 over 13. We worked that out before. Plus a, which is negative 10. Multiplied by t, which we just worked out to be 7. Put this whole thing into your calculator. Minus 10 times 7, and that's given me minus 45. So that means in this direction we have a speed of negative 45. In this direction we have a speed of 60. So we can work out this one by doing Pythagoras. So we're going to do 60 squared plus 45 squared. Don't worry about the negative because we're squaring it anyway. That is 5,625. Square root that, and we're going to get 75. So that was part B. We just have one more part to do. One limitation of the model is that it ignores air resistance. State one other limitation of the model that could affect the reliability of your answer. So we could say the fact that we use 10 as gravity. Should we do that one? So using 10 as, should I say gravity? Let's think. Yeah, I'll put as acceleration due to gravity. Acceleration due to gravity. Or we could have written the spin of the ball, couldn't we? Yeah, let's also write that. Was it a ball? Spin of the ball. You only need one. I'm just putting both so you know. Let's just check it was definitely a ball. Oh, it's a stone. Who's throwing stones off of cliffs? Right, let's change that. Of the stone. Okay, and that's your answer. So the examiner report said that this question was done really well. However, sign errors were common, resulting in half of the marks being scored for part A. So question 5 says, at time t seconds, a particle P has this velocity. We want to find the acceleration. So to do that, we're going to need to differentiate. So 3 times a half is 3 over 2, and then take away 1 from the power. It's going to be minus a half. And then minus 2t, so multiply by 1, which is minus 2, and then take away 1 from the power, so it's just going to be minus 2i. And that's it for A. That was nice and easy. Part B says, find the value of t at the instant when P is moving in the direction I minus j. So if it's moving in the direction of I minus j, this means that 3t to the power of a half is going to equal negative j. So it's going to be 3t to the power of a half equals negative 2t, which is just going to be 2t. So now we want to solve that. So there's different ways of doing this. I'm going to put it equal to 0. So I'm going to put 0 equals 2t minus 3t to the power of a half. And then I'm going to factorise it by taking out a factor of t. So that's going to be 2 minus 3, and then it's going to be t to the power of negative a half. Because if you multiply them out, you would add the powers, so it'd be 1 plus negative a half, which will give you a half. So that means that t equals 0, but looking at the question, it says that t is greater than 0, so that one isn't valid, so we can put NA. And 2 minus 3t to the minus a half is going to equal 0. So 2 equals this. Divide by 3. And then, because you've got a negative power, what we can do is we can write it as 3 over 2, and that's going to equal t to the power of positive a half. Then what we want to do is square both sides of the equation. So that's going to be 9 over 4. And that's going to equal to t. So that must be our answer. And question C, let's go and have a read. 3 marks for this question. At time t seconds, where t is greater than 0, the position vector P relative to the fixed origin O in r meters at t seconds. The position is r meters. Okay, full stop. When t equals 1, r equals negative j. Find an expression for r in terms of t. So to do this, we're going to have to integrate this here. So integrate our velocity. And the reason they've given us this is so that we can, because we're going to have a plus c, and then we're going to need to use this to find out that c. So let's integrate. And what was it? So it's 3t to the power of a half minus, was it 2j or 2tj? 2tj. And that's with respect to t. So add 1 to the power and divide by the new power. So 3 divided by 3 over 2 is going to give us 2. Here, add 1 to the power, so it's t to the power of 2, divide it by the new power, so minus 2 divided by 2 is minus 1. But don't forget, so this is in the a direction, this is in the j direction, and we're going to have a plus c. So now the question says, when t equals 1, r equals negative j. So let's substitute in t for 1. And that's going to equal negative j. So that means we want this to equal 0, which at the moment is going to equal 2. Can you see that? So we're going to have 2i. This is going to just be minus 1. So that means that c must equal minus 2i. Can you see that? Because this needs to cancel out, because in our answer we don't have any i's. So our final answer for r is going to be 2t to the power of 3 over 2 minus 2 in the I direction and minus t squared in the j direction. You can write that differently if you want. You could do like a separate I, but we can leave it like that. And part D, let's have a look. 6 marks, so it's going to be quite a bit of working here. Find the exact distance of P from O at the instant when P is moving with speed of 10. So we are going to do the square root of 3t to the power of, what was it? A half, all squared, plus, and then in the j direction, we have got minus 2t. We can just put that positive though because we're squaring it anyway. And that is going to equal 10. So let's square both sides. And that's going to equal 100. And let's multiply this out. 3 squared is 9. T to the power of a half, all to the power of 2. That's going to be t. And here, 2 squared is 4, t squared. So we've got a quadratic. Let's rewrite this as 4t squared plus 9t minus 100. And we can actually factorise this. But if you don't want to factorise it, if you want to use the quadratic formula, that's absolutely fine. Either way is going to be good. So if I do 25 here and 4 here, they will make 100. 4 times 4 is going to be 16, so 16t, and then 25t. So if we do 25t minus 16t, that will give you 90. And then we have 4t plus 25 equals 0. So 40 equals negative 25. So it doesn't matter about this one because it's negative, so it's not applicable. And here you can see that t equals 4. So that's the one that we want. So now that we know our time, go back to the question. Find the exact distance. So we look at our distance formula, which is here. And now we're going to substitute in t for 4. So r equals, and that's the I direction. Okay, put this into our calculator. 2 times 4 to the power of 3 over 2 minus 2 is 14. 4 squared is 16. So to get our overall distance, we know we're going 14 in the I direction, minus 16 in the j direction. Again, don't worry about negatives because I'm going to do Pythagoras. 14 squared plus 16 squared. That's going to give us 452. So our answer, our distance, is going to be the square root of that, which is going to be 2 root 113 meters. And that's your answer. So the examiner report said that part A was well answered by most candidates who realised that they needed to differentiate. But part B proved to be the least popular part of the question because the students struggled with this part here. So putting the, the 3t to the power of a half equal to the 2t. Let me know how you got on in the comments and make sure you like this video and subscribe to my YouTube channel.